I'm going to review oxidation reduction reactions in this video. That includes assigning oxidation numbers to elements and determining the element oxidized, the element reduced, the oxidizing agent, and the reducing agent in reactions. Scientists usually call these reactions redox reactions because we're too lazy to say oxidation reduction reaction every time. This is not a new type of reaction, it's a classification of reactions. Some of the reaction types that we've studied are redox reactions and some of them are not. The whole redox concept is based around oxidation numbers, which is just a form of record keeping for chemists. Oxidation numbers describe how electrons have been lost, gained, or shared as a result of that element bonding with other things. The first thing you've got to be able to do is assign oxidation numbers to the elements. So you have to know these rules and you have to follow these rules in order. First, free elements. That means an element that's in its standard state. It's not part of a compound. It's not an ion in solution. It's in its elemental form. These have oxidation numbers of 0 every time. They haven't participated in bonding in any way, so their oxidation state hasn't changed. Hydrogen is almost always a +1, except when it's part of a metal hydride, like NaH, sodium hydride. Then hydrogen is a -1. Oxygen is almost always a -2, except when it's in peroxide compounds, like H2O2, hydrogen peroxide. In a compound like that, two oxygens are bound together as one ion with a total charge of -2. So you have two oxygens with a total charge of -2. Each oxygen has an oxidation number of -1 in peroxide compounds. Next, for monatomic ions, their oxidation state equals their charge. A monatomic ion is an ion that's not a polyatomic ion. In NaNO3, for example, Na is a monatomic ion. NO3 is a polyatomic ion. Na's oxidation number in that compound would be the same as its charge. Lastly, the sum of all the oxidation numbers in a species should equal the overall charge of the object. If you're talking about a neutral compound, it has a total charge of 0, so all the oxidation numbers should all add up to 0. If you're looking at a polyatomic ion, all the oxidation numbers within that polyatomic ion should add up to the charge of the polyatomic ion. Try assigning oxidation numbers for every element in these compounds. In this first compound, MgCl2, we're dealing with two monatomic ions. So for both of them, their oxidation number is going to be their charge. So this Mg is going to be a +2, and each Cl is a -1 here. In the compound HNO3, we can go ahead and give hydrogen its +1 charge. Its +1 oxidation number. And we can give each oxygen a -2 oxidation number. Now to figure out the oxidation number of nitrogen, we're going to have to use this fact that the sum of all the oxidation numbers should add up to the charge of the object. This is a neutral compound, so the oxidation numbers should add up to 0. So if we have one hydrogen at a +1, we have 3 oxygens that are -2 each, so that's a total of -6. +1, something from the nitrogen, and -6 should add up to 0. Doing that simple math, we found that the oxidation number of nitrogen here is +5. In the compound CuSO4, copper is a monatomic ion, so if we figure out its charge, we know its oxidation number as well. In this compound, copper is a +2 ion. We can also give oxygen it's -2 as always. And then again, we'll have to add up the numbers to see what the oxidation number of sulfur is. 1 copper at +2, something from sulfur, and 4 oxygens at -2 each, which is in -8, has to equal 0. That means the oxidation number of sulfur has to be +6. When you look at the compound N2O, first, recognize that this is not an ionic compound at all, so there are no ions. You can't use that monatomic ion rule at all. So the first rule that we can use is the rule for oxygens. Oxygens are pretty much always -2s. If we have one oxygen that's a -2 and 2 nitrogens to balance that out, each of the nitrogens in this compound has an oxidation state of +1. In the potassium dichromate example, we can assign our potassiums a +1 oxidation number because that's a monatomic ion. We can give oxygen its -2 oxidation number. And then again, we'll have to sum the oxidation numbers to figure out the oxidation state of chromium. 2 potassiums at +1 each means this is a +2 here. We've got 2 chromiums, and then 7 oxygens at -2 each is a -14. This has to add up to 0. Of course, the number here that makes it add up to 0 is 12. But be careful in this example. When you give oxidation numbers, you're always giving the oxidation number of one atom of that element. In this example, 2 chromiums give us that +12 number that we've written up above. So what's the oxidation number for each chromium present? Each individual chromium has to be a +6 in this compound. In this last example, PCl3, again we're looking at a molecular compound. So we can't use the monatomic ion rule. We can't use the hydrogen rule, they aren't there. We can't use the oxygen rule, they're not there. If you get to the end and it looks like you don't have any rules to use, assign the halogen the oxidation number that matches its typical charge. Give those chlorines a -1 oxidation state here. If that's the case, and we have 3 chlorines at -1 each, this phosphorus has an oxidation state of +3. Oxidation and reduction are processes. They are processes that occur to elements during a reaction. Oxidation refers to a loss of electrons, and reduction refers to a gain of electrons. To help you remember that, use the mnemonic device oil rig. That stands for oxidation is loss and reduction is gain. These two processes cannot occur separately. For something to be reduced, for it to gain electrons, something must simultaneously be oxidized. For something to gain electrons, something else has to lose them. You can't have reduction without oxidation, and vice versa. If an element is oxidized, its oxidation number goes up. And if an element is reduced, its oxidation number goes down. Think of it like reduction equals the oxidation number is reduced. To determine the element oxidized and the element reduced in a reaction, you have to assign oxidation numbers to every element. Remember to use the rules for assigning oxidation numbers in order. So first, give free elements an oxidation number of 0. Where in this example do we have free elements, elements that are not part of a compound? That would be Na on the reactant side and Cu on the product side. So both of those have oxidation numbers of 0s. We have no hydrogens, we have no oxygens, so next we look at monatomic ions. they have oxidation numbers equal to their charges. Cu and Cl on the reactant side are monatomic ions. Cu has a charge and therefore an oxidation number of +2. Each Cl has an oxidation number of -1. Also, Na and Cl on the product side are monatomic ions. So +1 oxidation number for Na, -1 oxidation number for chloride. An element's oxidation number goes up during oxidation. Which element's oxidation number is higher on the product side than on the reactant side? Sodium. Sodium goes from 0 to +1, so sodium is the element oxidized. An element's oxidation number goes down during reduction. Which element's oxidation number is lower on the product side than on the reactant side? That's Cu. Copper goes from being +2 to 0, so copper is the element reduced here. Next, we need to talk about oxidizing agents and reducing agents. But first, think about the word agent, like insects are an agent for plant pollination. The insects aren't pollinated. The insects cause something else to be pollinated. Consider a travel agent. If you go to a travel agent and plan a big trip, who goes on the trip? You or your travel agent? You, of course. The travel agent helped you go on the trip. The same idea works for the terms oxidizing agent and reducing agent. An oxidizing agent is a substance that causes oxidation to occur to something else in the reaction. And a reducing agent is a substance that causes reduction to occur to something else. Remember that the oxidation and reduction processes always go together. Something is oxidized because something else is reduced, and vice versa. The oxidizing agent causes something to be oxidized by going through reduction itself. This substance gets reduced, and it causes something else to be oxidized. So the oxidizing agent is the reactant that contains the element reduced. Conversely, the reducing agent causes something to be reduced by going through oxidation itself. The reducing agent is the reactant that contains the element oxidized. In the reaction we looked at earlier, Na was oxidized and Cu was reduced. Our oxidizing agent is the whole reactant that contains the element reduced. Cu was reduced. As a reactant, that is in the compound CuCl2, so the oxidizing agent here is CuCl2, copper 2 chloride. You always answer with the entire reactant when you're naming the oxidizing or the reducing agent. The reducing agent is the reactant that contains the element oxidized. Here, that's Na. Some of the reaction types that we've discussed before are redox reactions, including synthesis, decomposition, combustion, single replacement. Double replacement reactions, on the other hand, are not redox. Every element maintains its same oxidation number throughout a double replacement reaction, so it's not a redox process.